Okay, back to resource efficiency. Well, DTC and resource efficiency. And we were halfway through the example on the trees washing up on the island. But let's just have a quick think again about the context. Okay. So, to frame the whole thing again, we're sort of trying to get our heads round this kind of data, right? If you really wanted to just simplify things for the whole course, kind of. And then we're leaving out the whole malthus bit at the start, and also some of the stuff at the end, and just focusing on the main part in the middle. It's like, what is behind these two graphs, and what can we learn about that, about policy and the future, okay, and sustainable economic growth and sustainable development. Okay. I'm going to shift this up a way. Okie doke. And then we started and we looked at just growth, didn't we? And we basically said, what did we say? The key take home from the growth is what drives growth? What does drive growth? Technological change, yeah. Not, for instance, capital accumulation. And this has been well known since 1956, when Solow published his model, which focused on capital accumulation and showed that it can't do the job. Okay. And then we looked at the DHSS model. And what if we think of Solow 56, what does DHSS do to that? Great. And the standard version of Solow 56, what's the production function in the economy? In a word, or two words? Right. So we've got this Cobb-Douglas with capital and labor, yeah? And then we add the resource and we stick with Cobb-Douglas. So you end up with like Y. You can write it slightly differently in terms of where you put the technological progress, but this is the way that I think makes most sense. And that what you get from this kind of formulation is that this could actually approach zero as long as these keep growing fast enough. Yeah. But then if you start thinking about making cakes and stuff, that's kind of, how is that going to work? So we need to dig deeper into this, right? Then another question is, and that's what we're starting to do now. What we've ticked off is looking at this as such, so to speak, per se, and thinking, so what do we assume about this in the standard version of DHSS?
The standard, like the classical, or the first one we did? The classical.
The classical one, yeah.
Okay, so it's a finite resource that is costless to extract.
Yes, great. You're doing awesome. So the standard, the sort of classical assumption is that. And so the only price of the resource is scarcity rent. The price, and there's perfect markets everywhere. So there's no monopoly rent anywhere either in the classic model. So the price of the resource is 100% scarcity rent. Because there are property rights over the resource stock. So you've got like an infinite in the limit, mathematically, an infinite number of resource owners, each with a tiny bit of resource, competing to sell it to the people who want to use the resource to make stuff with. And under those circumstances, what do we know about the price? We know how it's going to change over time, don't we? Go on, Elliot. No?
No.
Not in this one. Not when it's pure scarcity rent. Okay. Talk amongst yourselves. This is super important, actually.
And then
Get an answer. We said the interest rate.
It's going to grow at the interest rate. Yes. So maybe not a consensus, but an answer from one of you. Or whatever. That's the right answer anyway. So why is it going to grow at the interest rate? So put yourself in the position of one of these resource owners with the perfect market. So you have no strategic kind of ability to affect the price. You're just looking at the price of development. You have perfect information and you see the price going up very fast. You're thinking, whoa, well, I'm going to hang on to my stuff and sell it later. Or you see the price flatlining and you think, I'm going to ship this stuff and put the money in the bank. Neither of those can be equilibria because everyone else is going to thinking like you too, so the only way you can ever get an equilibrium is with this, if this is the interest rate row here. Okay, and this, to get the model working in a sort of solo kind of context, this has to be bigger than the growth rate here. So it basically means the price is rising. This is the price, isn't it? In the data, but according to this, it should be like this. And because there's a fixed factor share, that means the quantity has to be declining here. Because in logs, you add up the slopes. If you've got if we just say y is WRR, which is a simplification here, but then the slope of y has to be equal to the slope of this plus the slope of this. Okay, so you add up the slopes. So if WR is sloping like this, and y is sloping like that, the growth rates that is, then R has to be sloping down, negative slope. If you just think in terms of percents, it's pretty obvious. If y is growing 3% a year, WR is growing 5% a year, if this has to hold over time, then R has to be losing 2% a year, doesn't it? Okay. So this model is totally failing to match the data when we make that assumption about the stock. If we assume that, if we think about land instead, it makes a bit of sense. But then we're talking about land and not something exhaustible. We're interested in the exhaustible stuff. If you assume a vast stock with zero scarcity rent and extraction cost, you can actually get this. But then that's not telling us anything about what's going to happen in the future. And then we did this sort of future-oriented model where we could say, okay, we can actually build a model where you move through these different phases here, and you're going to get something. Okay. That's kind of fine and interesting, but we still got this problem that this production function doesn't really make sense. And so if we think of our best model, the final one, the tricky one, and we sort of said, we go through the phases, but even at the end when we're scraping the barrel, R goes down, but Y is hardly affected. So there's no kind of problem. And it has to do with the fact, why is Y hardly affected when R goes down? It has to do with beta. So how big is beta? We've been here before, right?
Is it at most 5%?
That's right, yeah, because the share, if you think of this as all natural resources, kind of, then it's like 3%, something typically. Then if there's an oil price spike, it might go up to about 5 for a while. So then, if this is 0.03, it's pretty easy to see, even if this is falling quite steeply, if these are still going up, it's not going to be a problem. And you can sort of say, well, that's how the data looks, but that's not good enough, right? Because you can't just extrapolate from some trends and say, oh, therefore, we want to know what's going on. Okay, the aggregate data is as if this is the production function, but when we look at firms, we know that their production functions don't look anything like this. So what is a firm production function more like in terms of the role of R? If you had to choose something simple, what would you choose for a typical firm, like a firm making cakes? How would eggs come into the production function?
I'm not sure I followed the question.
So we're kind of saying, look, this Cobb-Douglas doesn't make a lot of sense for a real firm.
Yeah.
So what kind of type of production function would make more sense looking at an individual firm, and especially thinking about this part, the resources, how do they come?
I think we talked about the Leon test.
Yeah? Something, if you had to choose some simple extreme, you'd think you wouldn't choose Cobb-Douglas, you'd choose Leontief. You'd say, well, you've got half the number of eggs, so we have to halve the number of cakes. Or maybe you could say, well, we can cope with we'll put fewer eggs in our cake. What if you've got half the amount of iron? How many hammers are you going to be able to make? It's tricky. Half the amount of fuel that you had last week. Well, the machines, half your machines have to stand idle. You're in trouble. Yeah, you're probably. The decent approximation would be, you lose half of this, you're going to lose half your production. As a first approximation, rather than this, which says lose half of this, you lose almost nothing of your production. Beta is so low. Okay, so we're trying to get our head round how should we understand, how should we think about the production function? And once we've got our heads around that, we can start to say, okay, so now we can start talking about the future and so on. If this stuff does actually start running out, and starting to understand what's been going on. Okay, so now we're up to speed and back where we were, pretty much. So shortly we'll go back into exactly where we were. The problem with these rooms, there's like no equipment. People nick the equipment. Oh, there were pens behind there. There's nothing to rub stuff off with, so I'll have to go and look for something. Never mind. Sorry, you just missed some math. I'm not sure how much you missed. Never mind. Okay, so what's this?
GT.
You had it, right, yeah. It's log of e to the gt, which is just like the inverse. It's like the inverse of the inverse. It's just gt. And that's what we just plotted. So when t is naught, log of 1 is naught, yeah, so it kicks off at naught. And the slope is g. So we're plotting that, and the equivalent WR log WR over WR naught is like the growth, a different g for the growth rate of WR times t and so on. So that's what we're plotting in those graphs. Yeah, so good that you asked about that.
Yeah.
Because it's like, I'd say in general in math, with these math stuff, if there's something like gnawing at you, I'm not really quite sure how this thing is probably quite simple, but I'm not quite sure how it works. It's a good idea to just go down, okay, how does this actually work? Because you're going to learn something from that as well, more broadly about getting confident in math. Okay. But the disadvantage is I totally lost what I was going on about. So does anyone remember where I was or what I was talking about?
I think we just said that we did the recap, and now we were supposed to go on with it.
Yeah, I think so. We're just gonna
Okay.
try and take an eraser then as I go forward.
Okay. Yeah, so we're focusing on understanding that production function, aren't we? That was kind of... So if we had Leontief, and that was end of story, you wouldn't expect this kind of result, right? And especially, yeah. So it seems like even if the short run firm level production function sort of ought to be something like Leontief, it seems like there's something else going on in the longer run. So if we've got, well, let's do CES instead. Well, no, we'll do Leontief. So we don't even need these then. Okay. And then, if you've got a fixed supply of R, say, and there's a just enough, and then AR goes up, so we get more efficient, but the supply of R stays the same, what's going to happen to the price of R? So you had just enough, it was nice and balanced, and then this went up, and this stays the same. What happens to the price of R?
Goes down
Right. How much?
very much.
Right. In the limit, kind of strictly, it sort of goes to zero. You can't sell the stuff at all, because someone else can always undercut you. It's in the limit of Leontief. So you would expect to see these sort of massive shifts in the share of GDP going to resources, depending on shifts in these. And we do see that in the short run, but not in the long run. Okay, so why might that be? And there's this idea that it's because of directed technological change. I can't remember how much we talked about this, but let's just talk, if we did talk about it, we'll just talk about it again, because it's super important, kind of tricky. So let's imagine that happened. Let's actually imagine that the supply of R went up for some reason, and the price nosedives. But then let's imagine that these are changing endogenously. Why? How come these change? How come they change? Is it just like random, what do you call it? Random draws, or? It's not random draws. So, can anyone say anything very general about why these change?
Research?
Right. And is the research done based on sort of random draws, or? So who's doing the research and why, kind of?
Okay.
Right. And they're doing it to earn profits. And if the price of this has gone to zero, how much money are you going to make by raising this?
Zero.
None, right? There's going to be no incentive to do research here if this stuff is free anyway. Why would you try to economize on that? And it turns out, and this is what I do in the video that we're scarcely going to go through, but you can set up a fairly straightforward model that makes quite a lot of sense, that says that the investments, if this is investment in knowledge, these Zs, are in proportion to the factor shares. Okay. So if imagine that labor, 95% of firm costs go to labor or labor capital. Remember, this is sort of, we've dropped capital or sort of combined it with labor, if you like. And 5% to resources, then this says that 95% of the effort, research effort, will go into improving labor productivity, and 5% will go into improving. Okay. But then you could imagine, if this share falls, then that 5% will go down even more, which means that this will start growing more slowly than before, which will tend to restore the share, won't it? Because this gets more scarce again. So maybe that's what's going on in the long run. That as soon as the share of one of these inputs falls, then firms stop investing in the knowledge to augment that input, and that makes it more scarce. Not because this gets smaller, but because we need more of it, because we're not very good at using it. Okay, so that could be an explanation for why in the short run we see something like this, but in the long run we see something like Koch-Douglas. That there's this mechanism pushing the shares back to some long run level due to the endogenous changes in these. Okay. And that is what we're actually looking at in this island story. Okay. Well, I don't think we ever really did that, did we? I don't think I ever gave you that story last time.
Yeah, I think
The
we did,
first part, maybe.
but I wouldn't mind doing it again.
Yeah, okay. So, where do we get to with the islanders? Let's do that super quick. We're going to just very quickly go through what we've got to. So we've got 10 people. So L is 10, R is 10, right? And of course, ideally we'd have units here, but I'm just doing notes here, so. And Y is 0.01. And we're going to say that epsilon is -1. Remember, they're poor substitutes, labor and resources. But we want to choose something simple, so we just go with that. And we kind of worked out, look, there's way more trees than they need to make one house every 100 weeks. So it must be labor that is limiting. And then we sort of, based on that, we made up some numbers, didn't we? For the 1 over epsilon. So we said, let's just make epsilon -1. If labor's limiting, then we can just drop this. And then we have y is ALL. L is 10, so then we know that AL is 0.001, don't we? And then actually we just said, look, how many trees would you need to make a house? And that's AR. I can't remember. Does anyone remember what we said? I guess if you've got notes, well, let's choose the same so that it fits.
Okay.
Was it point 1? Doesn't really matter. But I think it was point 1. Because there was a factor of 100 difference between them, I think. Yeah, it doesn't really matter. We'll go with point 1. Okay. So that's where we were, I think. Okay. So over to you guys. Think about this one. And then, I think I'm going to do some math with this as well. It doesn't seem to be in the slides, but. So the islanders invent sawmills. And remember, we're kind of ignoring capital, so it's as if they've suddenly got the sawmill. Okay, as well. Or they've done that investment. So remember before they had knives.
Mm-hmm.
So if you've got a sawmill, remember they're taking the trees, cutting them into planks, and making houses. So if you've got a sawmill, and there's 10 trees washing up per week, aren't there? If you've got a sawmill, can you handle 10 trees a week?
Depending on how big it is, I suppose.
It would have to be a pretty, not much of a sawmill, wouldn't it? If you can, there's 10 people to manhandle the trees and so on, and you've got some kind of a sawmill. So what do they need more of now in order to rate? And remember, once they've got the planks, they can whip the houses up in no time. So we're sticking with that assumption.
Mm-hmm.
So what would they need more of now to get more houses?
Trees.
Yeah. So what about the knowledge levels? So which do we need to change, or both? Do we need to change of AL and AR? Is it one or both?
AL that changed, right? With the song.
A.
L.
Yeah. How can you explain?
Because it's, well, you can see it as my tool, like it's my, I don't know how to.
Yeah. So if you think of the units, what are the units of
The
AL?
resource itself got more efficient. It's like my hours of labor that got
Yeah.
more efficient. Yeah.
So what are the units of AL? So Y is houses per week, isn't it? And L is workers.
House per worker.
Per week.
No.
Times workers is. So then if you think, the way to think about it is, imagine trees are totally unlimited. And then it's just Y is ALL. AL is houses per worker per week. L is workers. And of course, if trees are totally unlimited, and you switch from knives to sawmill, you can have a massive increase in production. So that's because AL went up, houses per worker per week went up massively. So what could we say for AL now? How many planks? Maybe you could cut up enough planks. Each worker could cut up enough planks for a house in a week. If we think that, then AL would be one. So part of the idea of this is to get you like economic models can seem so abstract, but actually they should be a good model and a well-explained model. You should be able to interpret it in concrete terms. Otherwise, there's a problem. It's typically often not done, especially in textbooks, but it really should be. Like with Solo, you know, it's just, well, there's this stuff, you know. For many people, it's not even clear that there's really only one product in Solo, which is both used for consumption and capital. And it's so weird that the textbooks kind of skate over it and try to sort of... But actually, because it's so weird, that's why you should be lifting it up, because it turns out that in certain applications it makes the model totally useless. And you shouldn't be aware of that kind of thing. Okay. So our new value of AL could be 1, for instance, couldn't it? If you had unlimited trees, each worker could cut up enough planks for a house in a week. What about AR? What's going to happen with AR?
Well, it should be the same, right?
So what are the units of AR? Again, imagine you've got loads of workers and it's just the trees that are limiting. Then we've got Y is ARR, haven't we? And R is trees per week. So this is houses per tree, isn't it? You think it should be the same? It could be.
Well, because you have the same size of the house.
What might... It could change. Why might it change?
More from the tree because you have a sawmill and it's like better
Yeah.
applied to getting
Yeah.
planks, I guess.
It might be.
But you get more
Bigger
planks
planks
from
per
You
house.
could maybe make thinner planks. Yeah. And then AR would go up, wouldn't it? Or maybe you're with your sort of... Somehow, I don't know how they make these planks with the knives, to be honest. But maybe they're incredibly skilled with their knives, and the sawmill actually just makes mostly sawdust. It's like super fast, but you like waste half the tree. Conceivably, yeah. So AR, I think it's much more plausible that AR would go up. But you could also imagine scenarios where it went down. Yeah. But we'll just leave it where it is. Because it's very clear that this is going to go up a lot, and AR is more, well, yeah, it might go up, might go down, probably would go up, but whatever, we'll just leave it. Okay. Well, what's going to happen if we haven't thrown any markets in here and stuff, but let's forget these parameters and just think about a market and imagine that actually this is a metaphor for a bigger island and the trees washing up everywhere and people grabbing them and then selling them on the market, and there's a labor market and so on. So we stick with these numbers later, but we're thinking now that there's actually a market. Markets for labor and the trees, perfect market. And then we've also got a representative firm making houses and hiring labor and buying trees. Okay. So what is that firm's profit maximization function going to be? Let's try and actually do better on keeping time. Why don't we take a break? And that is, we'll tackle that after the break. And then we're going to take first order conditions and work out factor shares. Theoretical expressions, and then we're going to put these numbers in and think about incentives to boost. Okay. So we take 50. Okay. So I want a profit function here. So what could that be?
For
for the firms building houses.
Yes.
So the revenue should be prices of the houses
Right.
times the quantity.
And we'll just normalize the price to 1.
Yep. And then costs would be hiring labor. And would the firms have to pay the ones collecting the trees, or could they
Yeah.
just grab the trees?
No.
Okay, so a cost of resources.
Yeah. So somehow there's this market for trees emerging, kind of. That people, yeah. Other people are grabbing the trees, lots of them, different people are grabbing them and then selling them on. Okay. And for now, in the full models, we're going to be we're actually going to need this. Because then we assume there's some market power and we look at marginal revenue and stuff. But I think at this point, I think we're okay just to do it this way. And then we're going to have to wave our hands around at one point. So, can everybody have a go at doing first order conditions in L and R, obviously? Yeah, I have gone through this. I guess it was in the video. Has everyone looked at the video, by the way? Okay, so just have a go at doing first order conditions. I'll cover it happily. Okay, I'm going to leave this running because otherwise I'll forget to start it again. Kind of like, yeah, okay. So you've got, if you do 1 over epsilon again, then draw the square brackets with a dot in the middle. So you're ignoring what's inside. And then think about the exploder. I can't remember how this is math. Not his strongest suit. So let me just do something. Let me just do some math for everybody. Okay. So this is just maths lesson, okay? So we forget this for now. Let's say you're differentiating y is x to the 5th. Okay. So what's dy dx then?
5 times x to the power of 4.
So it's 5x to the 4, isn't it? I didn't quite hear what you said, but I guess that was it. Okay. Let's write it like this instead, just for fun. Okay. Okay. No, that's wrong, isn't it? It should have been. I want something. Okay. Yeah. Okay. Yeah. Because you can see this, because this is x squared times x squared times x squared. Yeah, that's x times x times x times x times x times x, x to the 6th. Yeah. Okay. And let's differentiate that, but not by first turning it into this. Okay. what we can do is first do the outside and then go inside and multiply the two by each other. And what I'm doing here is not a proof, but it's just to try to convince you that this does actually work. Okay? We could prove it, but that would like take 10 or 15 minutes. It's not worth it. And yeah, you're not really into mathematical proofs. It's probably not going to help you. So let's just do this example and see that we get the same result. 6x to the fifth. So how do we differentiate the outside? We say, and let's put square brackets so it looks kind of the same. Okay. As this. So, how do we differentiate the outside? It's 3 times whatever was inside. We're kind of saving, we're environmentally friendly here. We don't want to use ink unnecessarily. And what power should we have here? 2. And then we go inside and differentiate this. So what's that going to give us? 2x. Yeah? And this is x squared, isn't it? So what's x squared squared? X to the 4th.
Oh, sorry. Yeah.
So we've got 3x to the 4th times 2x, which is 6x to the 5th. So like I said, it's not a proof, but it's just taking a really simple example and showing you that this works, kind of. I could prove it for you, but... so that's what you need to do here. Okay. So, back to you. I'll leave that up for... Have you got something?
I think so. So first we did like square brackets, and then so this should be the answer. I'm sorry if I'm writing.
This is great, but then you've gone wrong when you went inside.
Oh, because I tried to do like. Oh, okay. Let's try again.
So you did the tricky bit, right? Or what I would thought would be the trickiest bit. But this as well. What have you got? Where should I start? So you got...
Ja.
What are you crossing with now?
Oh, because I did.
Aha, you've done them both. Yeah, sorry, you did both, yeah. Yeah. You got it, yeah. Good. So this is exactly, you've looked at the video, right?
Yeah.
Well
I
done.
did this economist differentiation,
Yeah.
as you said.
Yeah, so you totally nailed that.
You can read it, what I wrote.
I think you've got it, yeah. So what have you got? Yeah. Right. But you need to be careful with the exponent on here, because that is raised to the epsilon, isn't it?
Oh, yeah.
Well done. Okay, excellent. Well done, everyone. So this is on the video. I'm pretty sure the DTC video, isn't it? But still, it's tricky. But yeah, we end up with 1 over epsilon times whatever was in the square brackets to the 1 over epsilon minus 1, which is the same as 1 minus epsilon over epsilon. And then we go inside, and if we're doing the L, then this just goes to naught, and we have epsilon times what we started with divided by L, which is a kind of neater way to do it. Then you don't have to worry so much. And the thing is, we want this L up on the other side anyway. So this, as so often when we do it like an economist, we're getting much closer to the solution we actually want straight away. Because then we've got minus WL equals naught. Take the WL over. Right. And then we can bring this L up as well. And we have that. Oh, and the epsilon and 1 over epsilon cancel. And we have that. And then for the R, we end up with this. Okay. And then if we're looking at the factor shares, we can say that WLL over WRR is ALL over ARR all to the epsilon. Okay, so you should be able to do this in your sleep. In fact, you should do it in your sleep. If you go to bed with a pen and paper, when you wake up in the morning, you should find this written down.
Is that a part of the exam?
Okay. So let's just play with these numbers. Oh, I rubbed some of them off, didn't I? So what did we get later? We had AL went up to 1, didn't it? And we stuck with AR as 0.01. Oh, 0.1. So if we call this just S, what's S here? It's ALL, so that's 0.001 times 10, that's 0.01 over ARR, which is 1. So it's 0.01 to the minus 1. So it's 1 over 0.01, which is 100, right? I mean, if you're doing this in the exam, you'd want to write down some steps, okay? But I'm pretty sure that's right. So what's that saying? It's saying that the firms are spending 100 times more hiring labour than they are giving to the people who harvested the trees and then are selling them on to the firms. Yeah, they harvest them from the beach, don't they? Does that make sense? We do a quick reality check. Does that make sense in this situation? Remember, with the knives? The trees are basically free, aren't they, here? Does that make sense? It does, doesn't it? Because the trees, remember, they're washing up all the time. There's absolutely loads of trees. And we just can't cut them up fast enough with our knives. So obviously, trees are going to have a low price. And so, but if we put the numbers in here instead, we get ALL is 10, ARR is still 1, so now we have 10 over 1 is 10 to the minus 1 is 0.1. So when we have sawmills, it's suddenly the labour which costs almost nothing. You're spending, for every crown you spend on labour, you're spending 10 on trees. This fraction is 0.1. So the people are just hanging around, the trees come in, they cut them up, and then in a couple of days and the rest of the week it's like, oh, what should we do? But the people with the trees are like, I've got a tree. I want 100 crowns. Okay. And then if we threw in some production functions for knowledge, and if we just, what I've done in exams, I'm pretty sure, is just say, look, just assume that ZL over ZR is in relation to S. assume that. I'm not asking you to derive that, which is what I did. I can't remember how much detail I went into, but on that video, it's quite tough. But then in the exam, I just sort of say, look, assume that the ratio of investments in new knowledge is given by the ratio of the shares. And then you've got some knowledge production function that sort of says AL T plus 1 is equal to ALT times Z minus some depreciation or whatever. And then you need to, and there's a certain amount of research labor, so there's 10 sort of workers, or 100 workers and 10 researchers, and how are you going to allocate them? Are they going to do research on labor productivity or tree productivity, trying to get more planks out of a tree, or find better ways to build a house with fewer planks, or then you can basically use this and this. You work out S, you work out how the research labor is going to be allocated, you stick it into the production functions and work out how knowledge grows. And then you can actually get these effects that I've been talking about out of a simple model where, sort of more trees suddenly start washing up, the factor share of trees goes down, right? Because of the poor substitutability, then there's less incentive to invest in tree augmenting knowledge. So this falls behind, this grows faster than this, which brings the factor share back up over time. So we can kind of do that in a simple examples. Okay. And yeah, I'm not going to take you through this in the lecture, but I think I think this is much easier for you to get a grip on, and it's giving you the intuition that I want you to have. And you've got the video. I think it doesn't. I do want you to look at that. Well, you've already looked at it, and maybe even look at it again. But the key thing is, I want you to get an understanding for what's going on. So one thing that's totally missing from this is, why would the firms ever actually do any research? Who's doing the research and why? Kind of. Because we just sort of say, oh well, we just assume this, and we assume that there's a fixed number of researchers, and they only ever do research. But in reality, of course, you've got resources. Should we put those resources, like labor or capital, whatever, should we put them into research? Should we put them into production? So ideally, we want a model that can capture all those trade-offs. And this model sort of captures a lot of them, but it's pretty tricky.
But that's what you did in the video, right? With
Right.
the Lagrange.
Yeah. And the point, a key thing in the model is that you've got a bunch of different firms making slightly different products, and therefore they have market power. And that means that there's an awful lot of different ways of looking at it. One way of looking at it is that they have some money left after they paid for their physical inputs, labor and the resource in this case. They've got some money left over. And normally you'd think, well, they're making profits, you're going to get entry. But in this case, they actually need that money to pay for the research. And if they don't do any research, they won't survive. Because they won't have any knowledge in the next period, basically, in the model. The following period, if this is 0, then they know they've got no labor productivity. they have to do research each period to be able to have any kind of productivity the next period. So that's the sort of structure of it. And then the math pans out. This result comes out of the math. And that is super intuitive, right, this? Do you kind of agree? Have you got the intuition behind this? Because that's really important. Yeah? That they are, the more a firm is spending on hiring labor, the more it'll invest in trying to use that labor more efficiently. Think of the extreme case with Leontiev or whatever. If it's spending nothing on the resource, why would it ever invest anything in getting more resource efficient? It will invest entirely in labor efficiency. Okay.
What was the S here? I just don't understand.
Right, sorry. S is this.
It doesn't stand for anything.
I'm thinking share. Share, the factor shares.
Okay.
But through most of the course, I don't use that terminology.
No.
So yeah, don't. It's good that you asked, but don't expect this to crop up, because S can sometimes be like a stock of the available resource or something. In the course, we more used it for that. So yeah, maybe I should just wipe this. It was just to make this link without having to write this out again.
So what you're saying in that top one is that depending on how you're doing your research, it will affect what factor shares you will have.
No,
No.
it's the other way around. Well, it does. It feeds back.
Yeah.
The factor shares affect how you do your research. That's what this is saying.
Okay. Yeah.
But then that feeds back into the factor shares in the long run, because how you do your research affects the factor shares. And the sector you do research in, its share tends to come down, because epsilon is negative, because of the poor complementarity. You do research in labor sector, then you invent sawmills instead of knives, and it's suddenly, we've got all this labor now with nothing to do, because they just win. And it's the trees that we need. If you did research on sort of tree efficiency, and initially you were using just trees to build your houses, you weren't even cutting them up. And then, so you just stick trees up, and then you invent a technology, just cut them into really thin planks, and you can make 100 planks out of a tree. So say you could then make 100 times more houses per tree. That would be research that raised AR, wouldn't it? And that might happen if trees were in desperately short supply and having a big factor share. Then, so you've got sawmills. No, that doesn't really make sense, because you're not needing to saw them at all, right? But if trees are in really short supply and they have to take a big factor share, then you're going to be looking for ways to make better use of the trees, aren't you? Like making thinner planks, for instance, like Janina was talking about. And if you succeed, AR goes up and the factor share of the trees will go down, if this stays the same. So you've got this compensating mechanism. Yeah.
I was thinking about this in the start there, like PI.
With this picture?
Yeah.
Yep.
PIYI, like that the price is a function of your production function. It was, that's how you write, like, if you're like a monopolist.
Yeah.
Because
Yeah. You have market.
You can, yeah, right, that's what
You have market power.
Yeah.
There's market power here.
Yeah.
So monopoly is a kind of a tricky word. So in a way, each producer has a monopoly on their product, but at the same time, the different products are substitutable for one another. So monopoly sounds very kind of definitive, so to speak, definitive or whatever. But it's more like they have market power. It's more, the more sort of, the better way to say it. When you have market power, the more you produce, the lower the price you get for your product, or the less you produce, the higher the price you get for your product, which is more the way you look at it when you you have the power to drive the price up by cutting production. In a perfect market, you just sell it for the same price, right? If you cut your production. Okay, so you should all be able to see the logic behind this, okay? Setting up a Lagrangian with these restrictions, yeah, which is the knowledge production functions. And then it's just revenue minus costs, what we've already done, but now we've got research costs as well as. So really, each individual step in this is, to be honest, pretty straightforward. But it's like when there's 500 steps, it's pretty overwhelming. Okay. And there are a lot of steps in this. Because there's also the step, which I've kind of ignored, about how much market power does a firm really have? Depending on this, there's an ether here in the consumer's utility functions, and to do the whole thing properly, it's an awful lot of steps. Yeah, so this is the consumer's utility functions coming in here, for instance. So don't worry too much about that. It's not like you need to be able to reproduce that. Okay. But what I do want to look at, I thought I fixed that. Is, let's see, what have we got here? Yeah. So, this. Okay. So, because this is really crucial now for actually understanding what's going on. So we're going to talk about this for a bit. Just have a quick look at those and have a think about what that is all about. Hope this is visible on the video. Okay. So I want some thoughts about those two equations. Or do you want to talk to your neighbour? No. Give me some thoughts. We can talk together.
I don't remember what this Greek letter stands for.
Okay, so that's zeta actually, but it's just a parameter, which basically says. So imagine zeta L is big compared to zeta R. What is that going to do? It's basically then saying that a given investment in the L sector is going to make less difference compared to the same investment in the R sector as well. So it's kind of weighting the productivities and investments in the two sectors. It's kind of saying that it's trickier to make labour more productive than it is to make trees more productive, if that was the case.
Yeah.
So the big Z's, that's like the we can think of it as the number of researchers in the L, trying to come up with labour augmenting, boosting the productivity of labour knowledge. And big ZR is the number of researchers trying to boost the productivity of the trees. So what's this phi doing there for starters, or phi?
Maybe it indicates that just because we do research, it doesn't guarantee that if one person do research, it doesn't come up with one idea automatically.
You're kind of on the right track. It's like if phi was 1,
Then that would be the case.
then if you double the number of researchers, what happens to the flow of ideas? It doubles, kind of, or the rate of increase. It's like ALT over ALT minus 1. So implicitly we've got some kind of discrete time here. And they're sort of doing research, and then in the next period they've got some knowledge. And the sort of increase in knowledge from one period to the next will double. But if phi is less than 1, then you've got some kind of decreasing return. So that's what that is doing. And in a lot of the growth models in the literature, they don't even have a phi. So implicitly it's equal to 1. But I claim that phi is actually quite important in some circumstances, and it should be less than 1.
Isn't it?
It's not just me, there are
Yeah.
others. It's called the stepping on toes effect.
Yeah.
That researchers tend to duplicate each other's work.
That's what's weird.
Yeah.
Yeah.
So
But
that's,
isn't it something called also, I think it's not as common, but standing on the shoulders of the giant, when it's
Right.
more than one, right?
so the standing on shoulders is the fact that we've got that ALT minus 1 on the right hand side.
Okay. Okay.
Because you're building on the existing stock of knowledge.
Mm-hmm.
So that's standing on shoulders. So good. But you're right, this is a crucial thing about the production function for knowledge, that we have this standing on shoulders thing going on. That we're building on the existing stock of knowledge. And so then focus on that, think about that, like what is really going on here in terms of standing on shoulders. Whose shoulders are we standing on? Kind of.
The last periods.
The last periods. But there's something more we can say. And of course the last period guys were standing on the period before that. So there's a kind of pyramid. It's like this sort of cheerleading. But the pyramid is the other way up. It gets bigger. There's one person at the bottom who came up with the first idea. So if I come up with a new labour augmenting idea, whose shoulders am I standing on? I think I'm going to have to look at the equation. Whose shoulders am I not standing on?
Those who are researching in resources.
You've got it, yeah. And if I come up with a resource augmenting idea, I'm only standing on the shoulders of the previous resource researchers, right? So it's like these two stocks of knowledge are growing completely independently of one another, aren't they? So imagine that this was actually, we've got a slightly different model, and we're doing research into making electricity. Okay, And there's two ways of making electricity. Oh no, we're doing research into generating power to do stuff in the economy, like grinding flour or shifting things around or pumping water out of mines or whatever. Making cakes. Okay. And up to around about the year 1900, the main way to do this, or the only way, is basically with windmills. Okay. So you have a bunch of researchers in the sort of windmill sector, or wind power sector, and you've got a bunch of knowledge in that sector. So let's just call that the L sector, okay, because we've got L and R. But then, in the year 1900, someone sort of discovers coal or something. And suddenly it's like, oh wow, this is way easier than the windmills. And what do the windmills look like in 1900? They look like the, what do they call them? The modern windmills that we use for electricity generation.
Wind turbines.
The wind turbines. Do they look like that?
They're standing by like rivers usually.
Or on top of hills, aren't they?
Oh, sorry.
Yeah, we're not on watermills here. I think you're thinking watermills, aren't you?
No, I think I thought we were talking about flowers. Sorry.
They're on top of little hills,
Yeah.
aren't they? And with wooden constructions with cloth sails, and you can have a horse to drag it around to face the wind. Okay, and then someone comes up with the idea of using coal instead, and someone invents a steam engine or whatever, and it's like, oh wow, this is so much easier. Let's forget the windmill. So then you get a big sector, we call that the R sector, building up knowledge in coal. Okay. But then in the year 2000, someone comes along and says, oh, this is terrible climate change going on. We have to switch back to wind. Okay. According to this model, what happens in the research? How can we describe what's going to happen in terms of the research that's going to go on? So let's think of the period as 10 years or so, or 20 years. Sorry, you were going to say something.
No, I was just thinking, well, so in the 1900s then, when we find out about coal, would all leave the sector of the windmills? Or would there still be some?
Yeah, so the windmills are all abandoned.
Okay, so we would have to go back to that, like, knowledge pool or whatever,
Yeah.
from the 1900s.
So when we decided to start wind power again, we would look up the old designs for wooden windmills with cloth sails.
Mm.
Okay. Then what's going to happen? Can you develop more on the theme? Kind of. Like how productive are these researchers going to be in the windmill sector?
Very productive in the beginning. Or
You might think so, but will they be in the model?
no.
Because they're still standing, they've just got the shoulders of the old windmill researchers to stand on, haven't they? So it's like, they get out, it's not just the old windmill designs they get out, they also get out the old windmill researchers' sheets of parchment and their quills and things, and start scratching their long beards and wondering how to improve these windmill designs. And they're totally blinkered off from, in the other sector, the modern sector, there's computers and modern materials and all sorts. They're not like separate, yeah.
So they would basically have to like invent what you would say like the wheel again, like
Yeah.
the research that would actually benefit, like that has been done in the R sector this model would say that, well, we would have to invent the computers again in the L sector. Okay.
So the point is, this makes absolutely no sense whatsoever. Okay. But this is what is sometimes it's embarrassing being in college. This is what's typically assumed in the literature. Okay. And then you can get these wacky results out. It's basically, with this assumption, this gives a lot of power to the directed technological change mechanism. Okay. Because you get this big, what we call the path dependence. And you get this big effect. If you shift, given this kind of function, these investments are absolutely crucial, right? So I'll give you a chance. Everyone's writing. These investments are just absolutely crucial, aren't they? And if you just sort of stop investing here for a while, then when you come back to it, you're way behind, and it's really hard to catch up again, isn't it? It's like what, but as Elin was saying, if you actually waited 100 years and did nothing, would it matter that much? In the wind example, how long would it take to sort of catch up? I mean, the fact that no research got done in wind between sort of 1900 and 1980 is more or less irrelevant, because that you can, with modern technology and and research tools, you could make that up in like a couple of days, because you're standing on these guys' shoulders. So actually the knowledge stocks are much more linked than this kind of thing would suggest. Because if you put absolutely no effort into this, it's going to fall way behind. But the point is that as soon as you start putting some effort in, you can catch up really fast. Okay. So it's not saying that the effects don't exist, they do, but they're just not nearly as powerful, nowhere near as powerful as this kind of model would suggest. And that there's a strong tendency for these to grow together, even if these differ a lot, because they feed off each other, or the one that's kind of behind, that ought to fall behind, gets dragged along anyway, because can benefit from the knowledge in the other one. If you start to fall behind, it's just so, with very small investments, like, if you want your wind technology to be sort of 20 years behind what it could be, if you were absolutely at the research frontier on wind and using the absolute latest technologies from elsewhere in the economy, that might be very expensive. But if you just want it to be 10 or 20 years behind, the investment you need to put into research to make that happen is like way, way lower.
Can't you just change the functions then so they depend on each other?
Yeah. And then the point is, we can do that, and then the properties change of the models. Okay. So with what I call the independent knowledge stocks, we get this property that the factor shares are constant. Because if the share of one of the factors goes up, we research more in that factor, that has a very powerful effect, and it brings the share back down. But if these tend to just grow more or less in parallel with each other, whatever, then that can't explain anymore why the factor shares are constant in the long run data. Okay. So there's papers saying, look, the sort of factor shares are kind of constant in the long run because of this direct technological change effect. But actually, it's not going to work if you have a realistic model. There's another way of getting at this, which is to say, look, if this is the true explanation, the DTC explanation is true, so we're trying to explain, we're back here again, yeah? So just give me some labels, this is WR, yeah, and that's R. So we're trying to explain why R tracks Y when WR is constant. So why is WR constant? That's to do with our extraction model and the stuff that we've kind of ticked that box, right? We did that kind of the last lecture. So okay, we're kind of fine with WR being constant, but why then does R track Y? When if we look at an individual firm, we should have something kind of Leontief-like, and then in which case we wouldn't expect it. The DTC explanation says, so what does it say? Let's just do the Leontief. So, if the shares are staying the same, what can we say about the growth rate of this compared to this? The whole term. That and that. How must they be growing?
At the same rate.
They must be growing at the same rate, mustn't they, in Leontief? And even in a CES with epsilon negative, that you get the same conclusion, yeah. And what do we know about, let's just ignore population growth for now. What do we know about, so if we just say L is constant, what do we know about labor productivity? That's going up, isn't it? That's what drives growth. So AL, that's been going up for the last 150 years. And what do we know? And that's driving growth, so that's more or less growing at the same rate as Y. Okay. What do we know about R?
Growth.
Yeah. At what rate?
The same as Y.
Yeah. So we've got sort of G, 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 and 0. So then what's the growth rate of AR? Given that the share is staying the same. Very good. So if this explanation is correct, then when we look at the micro data, it's basically saying, look, the reason why resource productivity doesn't grow, because this is basically saying resource productivity hasn't grown, isn't it? Because the amount of resources we need per unit of GDP is staying the same. Yeah. So this is kind of logical. The reason why aggregate resource productivity doesn't grow is because firm level resource productivity doesn't grow. Yeah. So this is widgets per ton of the resource, isn't it? The units here. So it seems kind of logical. But there's a massive problem with this. Especially if you think of what's the biggest inputs into the natural resource sector? What's the biggest part of it in terms of cash? Back to share. It's like energy, right? At firm level, has energy productivity grown? Massively. So if you think some of the data we have, it goes back to like the middle of the 18th century. What kind of technology we were using to get sort of useful work out of raw energy inputs, primary energy. Things like watts, steam engine, right? How much more efficiently can we get energy out of primary energy, useful work out of primary energy inputs today? It's kind of tricky. It depends on the context and so on, but I mean a rough order of magnitude kind of thing is maybe 100 times more efficient. So you could get, if you give me a ton of coal 150 years ago, I can get 100 times more useful work out of it today by sending it off to the latest coal-fired electricity generating station compared to what I could get out of it in 1850 by shoveling it into a steam engine. Something like that. If this was reflected in the overall economy, what would this curve look like? It would be like so the DTC story just doesn't hold water. It doesn't hold water in theory because the equations don't make any sense. And then when you start looking at the data in more detail, if you just look at the aggregate data, it's like, oh, we can explain the aggregate data. But as soon as you start digging a bit deeper, it's like, no, this is not what's going on. Okay. So what is going on? I mean, you've told us this before, so.
Me?
No,
No.
I was thinking of Ellen, but maybe you have too.
No.
I mean, you're only telling me back what I've told you, but. So Ellen can keep quiet.
Well, we talked about like the switch to consuming more energy-intense products, stuff like
Right,
that.
so this is the claim I'm going to make, that this is what's behind it, that it's actually shifts on the consumption side between different types of products. That's the claim I'm making in the course. But that's not far from universally accepted, but we'll see how that goes over the next 10 years or so. But that's what we're going to look at in the next part of the course. So let me just flick through these slides and see if there's anything I want to add to this. No, so this is basically what I've just taken you through. What I haven't gone through in detail is that based on the model with independent stocks, this kind of model, you can actually end up with Cobb-Douglas in the long run. You can show that you end up with constant factor shares. So it's as if this is the sort of long run aggregate production function, even though the short run firm level production functions are more like this, or CES with negative epsilon. Okay. I'm just thinking, because I'm going to stop the video and the next video is going to be on structural change. So I'm just thinking if I want to say any more. But I think we'll stop there and take a break. So.